All right.
Yeah. So let's see. Well, first off, apparently not. Let me ask one more time. Any questions from homework or anything? So it's all making sense? Beautiful. I want to, let's do this. Real quick.
Thank you.
Sure. Very colorless side. So the side says area and integral practice. Remind you guys. Right. You guys, we're all doing this side here, right? This side, the one without the blue? Yes. Just number one. Don't worry about number 2 yet. So we have the width. 3 minus 0 over 4. This n is 4. So I'm going to try to work us, this is almost exactly like the one we did together last time, right? I'm trying to lead us in the direction of the next big thing, obviously. It's what I'm always trying to do. What would my first xi be? 0. Well, 0, yeah, sorry. I forgot where it was going from. 0 is my first xi. Right? What would my next one be? 3/4, because what do? You start at A. What's A in this problem? 0. And to get, so the first one's A, and the next one will be A plus delta x. And then what's the next one?
1.5.
So the next one will be A plus 2 delta x, right? A plus, so it becomes this, A plus I delta x. Well, let's not worry about that. Okay. Not get too specific yet. So if I want to draw this in, here's 0. So my first rectangle, and then I'm going to go up to 3/4. Sorry, you guys ready? So now 0 is here, so then I can draw it over because I'm using left endpoints. Then I go to 6/4, which is otherwise known as 3/2, 1 1/2. So I can find that pretty easily. 3/2. So I base it on this height, and then I go over there. And then what's the next thing? 6/4, I go to 9/4, otherwise known as 2 1/4, right? So now it's based on this height, and then I go over there. And then finally, Thankfully, if I add 3/4 and 9/4, I get 12/4, which is 3, which is where I'm supposed to stop, yes? If you go too far, you've done something wrong. You calculated delta x wrong, something went wrong. Yeah, so now this will be my, I don't know why I'm supposed to get, because I put this too close. All right, so there's all supposed to be the same width, but that third one got kind of greedy on my picture. So what do you think? Is this an over or an underestimate, or is it going to be roughly right? Yeah, maybe a little under, but it looks like, especially from my terrible picture, it looks like that sort of takes care of that, and that sort of takes care of that. It should be kind of close, right? All right, really, is everybody? This is exactly what we did last time, right? Okay, so the area is the sum 1 to 4, the heights times the width. So the area, sum I equals 1 to 4. The heights times the width. I'm being a little more explicit here. But I mean, how do we calculate those heights? Like x1 is 0, correct? What would I do with 0 to see what the height is? The height is, of course, dependent on the output, correct? So what would I do with 0 to figure out the height of this first rectangle? Plug it in. So wouldn't I do that with each one of these? So that's all this is saying. Take each of your xi's and plug it in. That's all that's saying. Just being a little more formal. And does anyone remember what I could do with this? Do I have to take care of that each time? Take that out. So area, 3/4. So what do you get when you plug a 0 in? 4. Beautiful. That's the easy one. What's the next number we're going to plug in? 3/4, right? And again, be nice to yourself. Write this. So then you just got to go 0, 3, plug it in, right? And you could, and again, you could do your table set. You can make delta table 3/4. It'll spit out all of the crap you need. I don't know if anybody did that. What do you get when you plug a 3/4 in? Does anyone have that? What is it?
5.6875.
Sure. Sounds good. Looks about right. And then I want to plug in 3/2. I think this should be 6. I don't know. No, 6 point something.
6.25. 6.25.
And is there anyone right now that has no idea where these numbers are coming from? Tell me. It's okay. Tell me. It's all right. Everybody knows where those numbers are coming from. Okay. And then, of course, I'm going to plug in 9/4. Right. And when I plug in 9/4, what do I get?
Same thing, 5.6875.
Say again?
It's the same thing.
Same thing, yes.
Yeah.
You got a nice symmetry. Will that always happen? No. What happened here? How do I know that I don't need to do anything else in there? I don't want to mess myself up. Am I going to plug a 3 in? That's not the height of any rectangle. And what do I see right here that tells me I've got what I need? There's 4 freaking rectangles and there's 4 heights. There you go. I got 4 rectangles. So again, that's some of the biggest mistakes I see is people just kind of keep going. They just get so into blah, 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 blah. No. And then whatever the hell that is. 1 plus 2.4. Oh yeah, times 3. Shit. 4. Nobody's gonna help me. It's okay. 3.9. And then 1.4. 5.4 times 3 is 16.2. I don't know. I could be way off. Is it? Really? Roughly? Thank you, Brianna. So what do you actually get?
16.21875.
Yeah, so 16.2, that's pretty good. I know, I'm sorry, I apologize. And that whole process we did last time, right? I went a little quickly here, but you know, we did it last time. Nothing too major. What does that tell me again? What does this mean?
Area under the curve.
The area under the curve. So if I shade it in, I have approximated this area.
What's like the units for that?
Sorry?
What's the units for the area under the curve?
Did I give you any units? No. So you just leave it at that. If you want to be really, you can put units squared. So some problems will actually give you some units, but if it doesn't give you units, you don't have to put units. Yep. Yeah, I like it. All right, now, look at number 2. This is what we're getting into. Tell me this. Is that the right answer? Is that the right answer for the question, find the area under the curve from 0 to 3? Is that the right answer? The absolutely correct answer? No. It is the answer to number 1, which was estimate using 4 rectangles. That's an estimate. The actual answer is not going to be that, more than likely. Because we only use 4 rectangles, right? It's not going to be that high of a resolution. Now, our function's nice. It looks like it kind of filled in, so that's probably close. So what is the point behind what number 2 is asking us to do? And we, by the way, we don't know how to do this yet. This is going to be today's lecture. What is the point behind what number 2 is asking? What does number 2 do to make the answer better than number 1?
Infinite rectangles.
Yeah, we're using how many rectangles?
Infinite rectangles.
Infinite rectangles. Oh, shit. Okay, so let's do a couple of side notes, and then we'll work our way up to how the hell to do that. Okay, as soon as Jeff figures technology out. Okay, there we go. So there's a couple of things we have to, well, there's several things we have to kind of get before we start doing that. We talked about the summation symbol a bit, but we haven't really used it that much. Can you guys help me out? What is, how would you figure this out?
You would plug in 1 through 3 and then add them all.
Yeah, what is I doing? What do I be doing?
Adds up to like something 1 and 2.
Yeah, it's taking on the value 1. So again, I really want this to make sense. This is like function notation just with pluses in between several. So this is like f of I equals 3i. F of 1 equals 3 times 1. Plus, right? So this just means evaluate this expression for integers from 1 to 3 and then add them all up. That's what that means. It means a lot of shit all at once. Right? So I'll do 3 times 1, that's when I equals 1, plus 3 times 2, that's when I equals 2, plus 3 times 3, that's when I equals 3. Okay, that's fascinating stuff. Now, obviously we could just do that shit, right? But let me point something out. Okay. In this expression here, do I have a GCF?
Yeah.
What could you take out?
Right.
Yeah. And then you'd be left with,
The sum of.
right? And I love it. Somebody started, I love this. And that's 3 times the sum of what?
From 1 to.
I equals 1 to 3.
Yeah.
I. Yes? So really, look, all this shit, what can I do with this? I can take any constant out. It's just like factoring a GCF. It's just a string of sums. So if every single piece of an infinite of a long sum, not infinite yet, has a constant, the same constant, I can take that shit out. Now, what is the variable according to this summation? What is the variable according to this summation? What is changing? I. So can you take an I out? Sounds painful. Can you take an I out? That wouldn't make any sense. Do you understand that? Because I need it to be here so that this shit can happen to it. I can't take it out, but I can take a constant out. All right, let's up the ante. Obviously, the number answer, I don't give a shit about who's this point. Now, what about this? Something very similar. What do you got, Jeff? Yeah, I like it. Ooh, that's yummy. That's yummy. Go ahead and write, how many terms will you get when you evaluate this? How many terms will you get something plus some, how many terms? 3, right? 1 to 3. Right? Don't overthink this. What is the variable according to the summation symbol? I. So what's the only thing that's changing? Do we know what x is? No, we have no idea what x is. So what's the first term? X squared times 1, 11, right? So let me just put that, just to be pedantic. And then you get x squared times, what's I now for the next one? Yeah, I was 1 for this. Now I is, well, 2. 2 squares 4, I'm with you. Are you guys all with me, right? This is when I is 1, bam. This is when I is 2, bam. Now I do I equals 3, because that's where it told me to go. So it is just evaluate this expression at 1. Evaluate this expression at 2. Evaluate this expression at 3. But then the symbol says, add all those things up. And so what would the last one be? That's insane. Do I have a GCF? Yes, what's the GCF? X squared. So then I can write this as x squared times 1 plus 4 plus 9. And what is this? No, some of the number. Just like we did here. I squared. Yeah. So again, screw this shit. I can take this out. We are so not used to calling this a constant. But if somebody gives me an x, isn't this a constant? So whatever x is, this is a constant for each possible value of x, correct? In fact, what's the only variable in this expression? What's the only thing allowed to change? I. Yes? Do you guys see that? You need to be with me on this. This is huge. So this is the basic algebra of summation symbols. And really, I mean, this is all it is. This would become a string of things being added, so anything not dependent on I is a constant. It can come out. So let's do one more. And this time we'll do it shortcut. Can you rewrite that? Don't leave summation notation. What can you do? Is there anything you can do for this? Like, what do we do for this? Did we just take out a 3? What do we do for this? Take out the x squared, like Thomas said, constant, right? And again, what does the summation symbol think a constant is? What is a constant according to this do? What's the only variable it considers? I. So what is a constant to this do? Any other thing is not I. Yes? You tell me what x is, you tell me what y is, that's a frickin' number. So how can I rewrite this?
Take out the x minus y squared.
Yeah, just take an x minus y squared out. Bam, right? Now that doesn't, if you look at it, it doesn't feel ground shaking, but we're not used to the summation symbol. But this is just GCF, that's all I did, right? And our brains say x and y is a variable, but not according to this guy. He doesn't give a shit what x and y are. It's letting I change. It's not letting x and y change. So they're constants. Maybe? Maybe? Okay. One extra little thing. If I had to evaluate this, what's one little thing I could do? that is related to what we've been focusing on so far?
Probably take out the 7.
I could take a 7 out, yes? Okay, all right, 7, limit, it goes infinity. All right, so real quick, okay. Here's the final thing, and then we'll get into this. Ah, shit, well, damn, I'm sorry, you guys have any notes. What about this? Before you evaluate the limit, can you do anything? Say again?
Take out I squared.
Yes, why? Because what's the variable according to this limit? N is what's changing, yes? So I squared is a constant now. Do you understand what I'm saying? So anything not N can come out. And then you can evaluate this limit. By the way, what is this limit? Can anybody tell me what this limit is? Please. What are the degrees? Are they different, top and bottom? They're the same, aren't they? They're the same, right? N squared, if you multiply that out?
This one.
It's 1. It's the ratio of the coefficients, since it's equal degrees, yes? So this would just be I squared, because this is 1. Okay, what about this? Yeah, they're N. Yeah, let's just put infinity, yeah.
And times it plus 1.
Yeah, you can factor this shit out now, right? Because again, so this guy tells you what a variable is. Anything that isn't this can come out. This guy tells me the variable is. Anything that's not this can come out. Okay, like it? I love it. Equals I cubed, limit, blah, blah, blah. Just take that thing. All right, now. This is going to get trippy. I don't think I have my camera set up well. It's too bad for everybody. Those of you who decided to stay home. Boop. Okay. Let's look at this. In fact, I'll tell you what. Let's look at this first. Wait a minute. Sure, I like it. Look at this first. What does this mean? What does this mean? What am I doing? How would you write out? I don't tell you, but how would you start writing out what the summation looks like? When I is 1, what's this? 7. When I is 2, what's this? 7. When I is I'm going to stop at the nth one, right? Is there a short way to write that? 7n. Isn't that the definition of multiplication? If I'm adding 7, n times, there's the word times. Holy shit, 7n. Are you guys with me? So in general, the sum of I equals 1 to n of a constant is constant times n. Let that be simple. And again, it's just written in a different way than we're used to, but that's all that says. If I add up 7 n times, I get 7n. Of course I do, right? What do you get if you add up 3 4 times? What's the shortcut? Of course it's 3 times 4. That's all we're saying, yes? Okay. So let's get more interesting now. What about this weird shit? That would be what? No. No. Because now is this a constant?
Now it's
What's it look like? 1 plus 2 plus 3 plus 4 up to n, right? All right, so let's do a concrete example of this. Are you guys with me? This one was stupid easy because the inside doesn't change. So you just got to collect n7s. There we go. Okay, this one's harder because it doesn't stay the same. But I don't know if you guys have ever seen this before. Let's do this just to give a concrete example. All right. All right, everybody, just sit tight. Here we go. No, I'm joking. Blah 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 blah. Here's a bit of an urban legend to this. A mathematician named Gauss. He came up with this, but supposedly he was in grade school. The teacher said, everybody shut up, you drive me crazy. All right, sit down and add up the numbers 1 through 100. You cannot talk until you're done, or else I'm going to beat your bum, or whatever. Right? So they all sat down. Gauss came up 10 seconds later and said, here's the answer. And the teacher's like, so the teacher, 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 3. So it took him a long time, and he's like, how the shit did you get that answer? Gauss. Demon. I don't know. So it's like, has anybody ever seen this? The shortcut for this?
Yeah, but I don't remember.
You take out your tag before.
Yeah, what's 1 plus 100? Don't tell me any technology bullshit. What's 1 plus 100? Holy shit, what's 2 plus 99? What? What's 3 plus 98? 101. All right, so how many times will 101 be added to itself? 50. Right? Isn't there 100 divided by 2 pairs that make 101, yes? What does that come out to be? The most interesting answer, I think, one of the most interesting answers ever. 50-50, right? 50 times 1 is 50. 50 times 1 is 50. Yes? You don't need a calculator for that. I guess, so the sum of the first 100 whole numbers is 50-50. That is crazy. Yes? No? Isn't that neat? No? All right, whatever. So what is this formula? Where did the 100 come from? Why was it 100 up here? What would change here? Yeah, say it. N. Whatever n is, that would be the last number, right? So this is for anything. This would be n over 2 times. Now, where did we get 101 from? 1 plus, in general, n, yes? So we'll write it like this. And very often this is written as that. Same stupid thing, right? So the sum from 1 to any number, you can just do like this. Take that number, multiply by 1 more than itself, and divide that by 2. Kabam! Kabam! Okay. What if n is odd? Won't this come out to be a fraction? Oh shit! But won't this be even? So this will divide, so it comes out to a nice whole number, yes? Okay. Enough of that. So if I ever see this so like what we had earlier, real quick. Watch this. If I have the limit as n goes to infinity of the sum of I equals 1 to n of, it doesn't really matter, well, yeah, I over n squared. What can you do with that? Is there anything you can take out of the sum? Yes, the 1 over n squared, right? Can I take it out here? Can I take that out here? Because I can't go past him, yes? Because he sees n as a variable. So I can take this, 1 over n squared, I can take it out right there. And what is this? What did we just figure out this is? Yes? Yes? What does this do? N squared, that limit would be same degree, right? You need to be able to do this semi-quickly. 1. So this limit would be 1/2. Maybe? No? So we took the 1 over n squared out, because this guy sees I as a variable. The I was left inside. This, anytime I see this anywhere in anything, I can replace it with this. That's what we just proved. And then I can do the limit, because the limit cares about n. And do I see any i's left? No, because we know what the sum of I is from 1 to n. Maybe. This is exactly what's going to be happening to us. Okay. So then you might start to wonder, or not, what this is.
Isn't it just the same thing square? Or no?
Do sums work like that? Where you can take a square out? No. See? No. So I really want you to understand, this is not going to be that simple because this is a sum and this is a multiplication, right? I times I. So they don't play well together immediately. Yes. Can you write out what's the first few terms of this?
One square, two
So
square.
1 plus 4 plus 9 plus 16 plus 25 plus blah, blah, blah. Real quick, how far apart are these? 3, 5, 7, 9. Excuse me. No, maybe. Every square number is an odd number away from the next square number, and they go successively. Has anyone ever told you that, or you ever noticed that, or do you give a shit? I don't give a shit.
I just randomly thought that one day break out.
Nifty. Okay. Now, watch this. So I really want this to make sense. Let me write this like this. If n is 1, let me just use the letter S for this, right? What would S be? What would the sum be? If n is 1, don't I just get this? It would be 1 to 1, so I get 1. If n is 2, then what am I looking at here? 1 plus 4, yes? If n is 2, I'm going to go out to the second term. Are you guys with me? And that's 1 plus 4 is 5. Holy shit. If n is 3, what will this sum be? It'd go out to the third term, right? So let me be a little more specific. S1, S2, S3. Kind of makes sense. The first sum would be 1. The second sum would be 5. Third sum would be 5 plus 9. Is that cool? 5 plus 9? 14. Let's do a couple more. What would S4 be? It would be 14 plus, yeah, because this is 14, right? 16, 30. What would that's 20, I think. Why not, Jeff? I can't remember what it did. Yeah, sure, okay, now. All right, listen. I'm about to do something really strange, and you're like, normal day here, Jeff. You're not going to have to do what I'm about to do yourself. I just want to explain, I'm not going to prove, but I am going to explain where this guy's short way to be written comes from. Yes? Okay, so watch this. For some reason, now just go with me on this. Trust me. Just, I don't know. Green, you don't work too well, do you? No. Damn it. Come here, Billy. Let's see what you do. Oh, look at you, dude. I know. No. Just, maybe don't even write this down. Yeah. Okay. I'm gonna, for some reason, just wait until I get there. Okay. I'm gonna multiply each of these by 6. Now, there's a lot of work that went into what I'm about to show you, and it wasn't done exactly like this. This is just my quick way to show you why it sort of makes sense. Multiply each thing by 6. So I get 6, 30, what is that? 84? And then 180, yes? And you're all like, yay, Jeff. Now watch this. This is where shit gets nifty. Factor 6 for me. Factor 6. Okay. Prime factor. 2 times 3, right? Yes? So let me write that as 1 times 2 times 3. Factor 30.
1 times 5.
5 times 6. So 5 times 2 times 3, right? So we write that as 2 times 3 times 5. Yes? Maybe? Factor 84. Four goes into it, yes? 21 times. So isn't that 4 times 3 times 7? So if I write it like 3 times 4 times 7, do you start to see a pattern showing up? This was 1 times 2 times 3. This was 2 times 3 times 5. This was 3 times 4 times 7. So what do you expect this to be? 4 times 5 times 9. Is it? Is it? Yeah. So what would you expect the next number here would have been if I would have kept going? 5 times 6 times 11. What is 5 times 6 times 11?
330. 330.
Yeah, 330. So let's see. What would S5 be? That would have been 30 plus 25, right? 55. And if I multiply that by 6 like I did all the other ones, what's 55 times 6? 330. Okay. Now again, you never have to do what I'm doing. Isn't this weird? Would you ever think to do this? You would never think to do this. Yes? And that's not saying anything bad about you. That's just freaking no human, or very few humans would think to do this, right? Now watch this. This is so cool. Okay. I don't know if I'm getting all this. Get out of my way. Go over there. Sit there. Keep it. Keep it. Boop. Keep. Okay. Get out of here. So watch this. When n is 1, this is 1 times 2 times 3. When n is 2, this is 2 times 3 times. So this and this is easy. When n is 1, n times n plus 1, yes? Yes? Do you guys see that part? Times an odd number. And then I get, when n is 2, n times n plus 1 times the next odd number. So now we just got to figure out, how do I write odd numbers? What are even numbers? Things that are divisible by 2. So I can write them as 2n. And aren't odd numbers just one more than that? 2n plus 1. Let's see, when n is 1, I get 1 times 2 times 2 plus 1, 3. Bam! When n is 2, I get 2 times 3 times 2 times 2 is 4 plus 1 is 5, right? Okay, so what does this represent? That represents these, yes? Yes? So what represents these then? That's what I need. Jeff, you missed them. What represents these? What do I have to undo? All right. So, now, the other option for today would have been I just tell you what the shit it is, but I wanted to go through that. So I know now, I know the sum of I, we did this earlier, is this, right? Now we know the sum of I equals 1 to n I squared is this. And the last one I'm just going to tell you, just because that would be, you could do something similar, yes? This one is really weird. The funny thing about this one, I want to see who reacts to this one. This is a very humorous one. What is that? Isn't that? So isn't that what you thought this was going to be? Yeah, but again, sums and exponents are weird together. Okay. So what the shit does this mean for us? Okay. Let's come back to that sheet. Let's come back to this sheet. I'm not going to do this on the overhead. Number 2, right? I'm going to do this up here on the board. I'm going to leave these here. We're going to need them. And real quick, let me do a concrete example. If I did the sum 1 to 3 of I cubed, we can actually calculate that, right? What would the first term be? 1. Then I is 2, so this would be 8. Then I is 3, so this would be 27. And I get 36. Now, what is n? What's the value of n? 3, yes? What do I get here if n is 3? 3 times 4 divided by 2 is 6, right? Squared. Just flip it, 36. All right, good. I'm glad I did that because, again, that's the concreteness behind this shit. You give me an n. If n was 80, do you want to do it this way? Wouldn't it be much better to do it this way? 80 times 81 divided by 2 squared. Bam, right? Kind of nifty. Okay. What really sucks, well, it doesn't suck. We teach math in an order that makes sense logically to build, but it is not the order in which we discovered things. You understand what I'm saying? So we don't teach math like history. We teach math like, we discovered this here, but it makes more sense to talk about that first, and this we'll put there, and then we can build, right? So to be honest, sure, whatever. A lot of the early math was looking at sums. Derivatives were discovered by looking at sums, for example. It's a really interesting history. Not really discovered, but they kind of naturally came out of some of the work they were doing. That's all I'm going to say about that. I'll keep talking. Let's look at this guy. So I'm giving you f of x from 0 to 3. And I want to evaluate this. Can somebody tell me again, just for the sake of remembering what this is built on, physically, what is this and what is this? Visually, geometrically, yes?
That's the height of the curve.
Height,
And that's the base of it.
that's the base. So this is an area, and if I add up all the areas, I get the complete area under the curve. All right, so don't forget that's what this shit is built on, right? Okay. So what do I need to figure out? What does this need me to figure out from what I'm told so I can plug shit into this? What do I need to figure out? There's 3 things, basically.
Base at infinity. Is it the height and base at infinity?
The height, right? Which has got 2 things I got to figure out. Don't I have to first figure out xi and then plug it in? You guys see that? And of course, what's the main thing I need there at the end?
Yes.
What is the formula for delta x? You guys remember?
B minus A over
You. Yeah, b minus a over n. Do I tell you what n is in this problem?
Yeah.
I don't say infinity. Don't. N is something, right? I'm going to let it go to infinity, but that's the last thing I worry about. So I didn't tell you what n is. So it would be 3 minus 0 divided by, I don't know. Yes? I can't put a number there because I'm letting n go to infinity. It's not a single thing. Okay, so far so good. Now obviously, what we're doing right now is we're getting away from concrete number of rectangles. We're going to letting n go to infinity, infinite rectangles. I don't want to deal with infinite rectangles directly because do you want to? No, so what I'd rather do is deal with that, some unknown number of rectangles, figure out what that is, and then do that. That's what we're going to do. So how many rectangles do I have? N. So it's 3 over n for the width. Now let's see who was listening earlier. We can do this. Let me see if I can make this make sense. Since I'm letting n go to infinity, what's going to happen to the width of the rectangles? It's going to basically go down to almost 0. It's going to go down to dx, yes? Does it really matter then if on the way to that I use left endpoints, right endpoints, midpoints? No. So we could build this process using any of that shit. We decided to build this process on left endpoints just because. It made it easier, right? So, can somebody tell me, what would the first thing here be? It's the same as what we did on the first problem. What's the very first input? 0, right? So in general, what are the xi's? So the first one would be 0. How would I get to the next one? What did we say? Remember how we said? Why did I go to 3/4? Because that's the width, right? What's the width now? 3 over n. So how would I get to the next, how would I get to x2?
0 plus 0.
Then how would I get to x3? I would add another 3 over n. So I end up adding right? So that's capturing. Why do I have to have a variable expression there? Because I'm not saying which x2, x3, I'm saying xi. Okay, maybe. Where's this right endpoints? Okay. Now I've got, so we got delta x, check. We got xi, check. What's the last thing I need to do? F of xi. That's what I really need in there, right? So, but I can't do f of xi until I figure out what xi is, so I can shove that shit in, right? Just to use the technical lingo. Shove that shit in. All right. So what is f of xi? Well, it's f of 3i over n, right? All right, and what does f do to anything? Anything I shove in there, what's it do? It does this, right?
Yeah.
So it'll be 4 plus 3 times that, right? So 9i minus this thing squared. So it'll be 9i squared over n squared. Is that cool? So this is the order you do things in. The width gets things going. Xi is built on the width. Will this always be 0? Why is it 0 here? Because we started at 0. What if I start at 7? Then there would be a 7 there. Ooh. And then, so this builds this, and then this gets shoved in there, right? All right. So what does this look like now? Oh, I know. I could feel some of you guys like, let it just stop. Even right now, this isn't making it better. This joke you're doing. Okay. But it's a building process, and each step is not that hard. But now when I put it all together, it's going to look gross. So f of xi is that. And then times delta x, which was there. So this is f of xi, and this is delta x. Exciting, right? So this is the equivalent of the limit definition of derivatives. We're going to very briefly be here, right? Section 5.2 basically. 5.3 we immediately get into shortcuts. So you only have to endure this for a tiny bit. So what can we do with, can anybody tell me, do you guys see anything you can do in here?
Take out the 4.
Say again?
Take out the 4.
I can't take out a 4 because is it a common factor? Is it multiplying this thing? No. But what is?
1 over n.
Even better.
3 over.
I can take a 3 over n out, can't I? Isn't that GCF? Isn't that so? I can take a 3 over n. How far can I go with it?
Stop at the limit.
Here. I can't go there because this thing's n is a variable, so I can't go past that. I could take the 3, but screw it. I'm just going to 3 over n. I'm going to take that 3 over n. Just going to take it out. GCF. So at least an I out here, right? So I'm going to multiply the I in. Is that cool? So I'm going to have 4i plus 9i squared over n minus 9i cubed over n squared. Do you guys see anything related to these? There's a I and a squared and a I cubed. Oh shit. Oh shit. Right? So there is something for I4, but we're not going to, don't worry about it. So then I get limit, n goes to infinity, 3 over n. All right, now watch. How do I say this? commutativity, and associativity. Right? If I do 7 plus 3, isn't that 3 plus 7? If I do 7 plus 3 plus 4, isn't that 7 plus 4 plus 3? If I had 7 plus 3 in parentheses plus 4, could I move the parentheses over? All right, so what the shit am I talking about? Isn't this sums of sums? Couldn't I sum this shit up first, and then sum this shit, and then sum this shit, so I can break the sum up? Yes? Maybe. So if I had to do x plus y plus z plus 2x plus 2y plus 2z plus 3x plus 3y plus 3z, do you have to do it this? Thankfully, no, because you can't do shit, but I can do, this and this and this I can put together. Right? So what I'm saying is the same, these are like my x's. So let me add these up first, plus add these up next, minus add these up last. Oh, and I can feel it. I can feel it. All right. Take a second. Look at the whole board. Right? Isn't it disgusting as shit? All right. Realize if you just look at one line to the next line, how much actually happened? Not that much. Yes. It's when you look at the whole thing, you're like, oh, get dizzy. What can I do now? Look, focus on just this. What can I do with just this? Sort of. I'm almost there. What do I have to get out of the way first? The 4.
Right here.
Yes? All right, so let me do this. And obviously you can kind of understand that several of the steps I've written, you don't have to write. You can kind of put a few of them together. But I'm going to do this all the way out. I can do something similar here. What can come out of this one?
9 over n.
9 over n. I love it. Because again, the I shit's got to stay in. Right? You can do it, Jeff. There you go, buddy. And then minus. What comes out of here? 9 over n squared. Oh my goodness. You guys excited to do like a bunch of these? Oh yeah. And do you see, do I know what that is? Yeah. Do I know what that, yeah. And then I can do limits, because then all I'm gonna have left once I replace this is a bunch of n shit. And then I do limits. And the better you understand the pre-calculus level idea of if the degrees are the same as the ratio of the coefficients, you can do those limits quick as shit. Okay, so let me do this. I'm gonna erase. You guys have this yours, hopefully somewhere. I got it on a sheet of paper too. Erase these two, because this is the one I can't ever, well, this one's the one. Oh yeah, the I squared is the one I can never remember. So you guys can help me out. So let me see, so I got the limit, and goes to infinity. Over n, and what was this? Oh, sorry, 4. Wait, times 4 times n times n plus 1 over 2. That's what I can remember, right? You see that? So I just replaced this with what it is, plus 9 over n times sum of I squared was.
And times n plus 1 times 2n plus 1 over 6.
I've given myself not enough room again. I love it. You're awesome, Jeff. Plus, I'm sorry, the last one's a minus 9 over n squared, and this one is the nice one. It's just this guy squared. There's a lot of parentheses, Jeff. Okay. Yeah, there you go. So let's see, you're going to limit, and goes to infinity. Of, let's see, I'm going to bring this 3 over n in, so let's see if we can handle this. 12, well, let's see, can we really handle this? 12 divided by 2 is 6, is that cool? Right, 12 divided by 2 is 6. n plus 1. I could have killed the n, but I'm just going to put it there. So 12 divided by 2 is 6. This times this over this. Bang! Plus 3 over n times 9 over n, 27. Well, let's see, can we do this? Screw it. 27 n plus 1, 2n plus 1 over n times 6. Right? Just distributing. Minus 27 over n cubed. Okay. Did I lift something up? N squared. I feel like I left something up. Oh, that's gonna suck a lot, Jeff. Oh, I did. I totally did. Oh, I love it. All right, so here's something. I did not do this on purpose, but I'm not even gonna try to claim that I did. Do you guys notice how? What even happened there, Jeff? What have you done? Oh. Let's see. Over n. Give me just. This is the best time in the world. Is when I think I have forgotten something. Let's see. Something got lost. Hold on, guys. All right, all right. I really want this to make sense. What should happen here? I'm trying to see where I lost something. You guys are like us. Yes.
We take out the all three that have the same like n.
Yeah. So what should happen here is this should be the same degree as the bottom. That should be the same degree as the bottom. This should be the same degree as the bottom. I can see one. Oh, I love this. You see? Oh, right here. No. That's right. Okay. There's that. There's that one. Damn it. Let me see. Where? All right. So. What needs to happen on this step, or what's telling me I've made a mistake, is that the degrees here should be the same. Otherwise, what would this limit me? Because right now, this is a degree 2 and this is a degree 1, so this would be infinity, right? And I know the area isn't infinite, yes? So I know this should be the same degree. Now somewhere I have left out, somehow I've left something out. Let's see where it is. All right, let's do this. All right. Let me point out, look at the other side of that sheet. Did I give it to you? I think I've given it to you yet. Oh yeah, I did. So this one with the blue rectangles. I've done the same stuff, but with the expression 4x. So there's a fully worked out problem for you. You can see the useful sum formulas here, right? Okay, because those will show up. Let's see, I don't see what I lost here. What did I lose? Somehow I lost an n somewhere. How did I manage that? Let's see. Let's see here. Did I miss? Oh. Okay. All right. I'm kind of happy I made this mistake. Sort of. Kind of. I don't like making mistakes. I made what's really funny is this is sort of a not so common mistake to make, so it's kind of, I decided to be unique. Can somebody tell me, what is delta x again? It's one of the very first things we did. What is delta x?
3 I over.
No. So Wesley, you made the same mistake. What is delta x? 3 over n, right? Isn't that the delta x? The width shouldn't change, yes? Now, of course, what did I put here?
3 I.
So you see how I gave everything one more I than it was supposed to have, right? Okay. I'm not gonna make. So what would happen then is here, that should have been like that, right? It's the worst thing that can happen to a teacher, by the way. I hate that this happened, but it happens. Do you guys understand what's happening? So I put one extra I there because I wasn't careful by looking back here. My brain was stuck on, we just did this, so I'm thinking 3I over n. Okay. It's not, I see it sometimes, and of course I decided, why don't I just go ahead and do that? So what kind of sucks about trying to salvage this problem is that would make this gone, that would make that one less, that would make that one less, right? So this will be, we could have just left the 4 in there, to be honest. This would be I, this would be I squared. So then this wouldn't be here, right? And again, if you don't want to try to salvage this, I understand. But remember, what's the very first useful sum formula for like the sum of 4? 1 to n, it would just be 4n, right? And then this would be the I squared, the I, so that should have been this. So basically I was just 1 off. So then this would have been from the I squared, so this would have been become a 2n plus 1. So I just had this here, and then I had the I cubed one there because I gave one too many I's to everybody. So let's see if I can kind of salvage just a little bit. All right. So here I get 12. That's awesome. Right, the n's cancel. So here I get 12. There I get 27 n times n plus 1 over 2n squared. You see how the degrees are the same now? And here I get 27 over n cubed times n plus 1 times 2n plus 1, crap, over 6, running out of room. So this limit is easy. What's the limit of 12? 12. This one, what's the limit of these? 1. So I get plus 27 over 2. And then this one, now this is interesting, this is where you gotta be careful. Wouldn't this be 2n cubed? So it'll be 2n cubed to n cubed would give you a 2, a limit of 2. 2 divided by 6 is 3 down here, and the 27 is 9. Oh my God. So then you get 3 plus this, which will be 16.5, is that right? Okay. Do we have a way in our calculator to get that exactly? Yes. What do I do? In the calculator, kind of double check this. I'll let you guys keep copying that down. One silly little mistake. But just to remind you guys, remember in the limit definition derivative, the h's had to cancel? Remember that? Because you had an h on the bottom, which is making it indeterminate. So that h's had to cancel. So if they didn't cancel, you know you made a mistake. That is your check right here. If the degrees aren't the same, you know you made a mistake. Right? Yeah. I'll keep showing you. Oh, let's do this. in the calculator, if I put that function in, someday this will happen. There we go. So let's put that function in. 4, what was it, 4 plus 3x minus x squared. Assume 6 just to start off standard. There's the good parabola. And then if I go to count, which one was it that relates to the infinite sum?
7.
Yeah, so remember, letting the number of rectangles go to infinity, I just make the summation symbol become a long S band. Right? So if I do number 7 and I tell it go from 0 to 3, 16.5, right? Which is the exact right answer. So anything, and what did we get again for the, what was it, 4 rectangles?
16.287.
Yeah, pretty good, right? And it was only 4 rectangles because, again, well-behaved function. But that is the perfectly right answer. Now, see if I can salvage today. And again, it's one of the worst things ever. I hate. Anyway, silly little mistake. Kind of nice because now you're going to know to not do that. So I'll pretend like it. Yeah, I did it on purpose. Look at the last part number 3. Let's do this together. This is the thing we have to prove next. What is the antiderivative of that function we're working with?
4x plus
Yeah.
squared.
Let me catch it. So big ass f of x. 4x plus. We got to make it squared, right? So they have to be divided by 2. Minus something similar happens here. Now let's do what's big ass f of 3 and big ass f of 0. Big ass f of 0 I'll do. Oh, that was tough. Now I left off something. What did I leave off here? Well, we'll see why later. It's not going to matter as much when we're doing these what's called definite intervals, when we go between definite numbers. Let's see what f of 3 is. You'll see something very similar here. 3 squared is 9 times 3 is 27. 3 cubed is 27. Yeah. Look at this. 12 plus 27 over 2 minus 9, right? Yes? So that is, I got email. 16.5, of course, right? So what is f of 3? Big ass f of 3 minus big ass f of 0 happens to be the same number as the area. So it looks like, now this is one example. Could we have just gotten lucky there? Shit, oh yeah, that happens all the same time. But if we were to do this with any function anywhere, this would happen. So what we have to prove next is that the antiderivative of a function directly relates to the area under that function. Because what we just did is, in one step, we got something to plug in and I got the answer, and it's equivalent to all the work we just did. Do you understand what I'm saying? So this is like learning derivative shortcuts instead of using limit definition of derivatives. Okay, like it? Let me see. Okay, I can do one more thing. Okay. Do one more thing. Let me see. I can kind of do one more thing to get us ready for next time. Let me do this. I gotta plant this seed in your brain, which sounds like a horror movie, but too bad. I'm gonna define a new function. When's the last time you learned a new function? Like learning sine of x, or learning square root of x, or natural log, right? It's been a while, yes? So it's time. Let's learn a new function. Too bad we are. It's not a democracy. This is going to be basically the funkiest function you've ever learned. Recall, just to really put this in your brain. This, we're not doing this yet, recall this. Just to really put this in your brain. Right. This notation can be written as this notation. This means the area under F from A to B, which is what this means, right? Why can't you see A and B here? Because it's in there, right? B minus A over N. Okay. This one explicitly tells you what the shit you're doing, which is kind of nice, right? These mean the exact same thing. What we just did, the calculator shows that. The new function shit. So basically what this is, you give me g of t and I have a. This function, if you plug in 3 here, it will tell you the area from A to 3 under G. What if you plug a 4 in? A to 4. So for every value of x that you can think of, it's just going to tell you, and you can go backwards too, which is kind of become negative area, which we'll talk about at some point. I keep not talking about it. So that is truly a variable. What's really weird is the function itself is a constant. I'm given a function. I really want you to understand. Here's the function, I gave it to you. Does that function change? If that's all I say, here's a function. That was neat. If I give you a function, can it suddenly change itself? Does it? No. So this function, in a sense, is a constant. If I give it to you, it's sitting there. This function is sitting there, correct? Just sitting there. What's changing for this here is how far I want to find the area up to. Yes? Yes?
So is the function the curve, or is it like every single point inside the thing?
Which function are we talking about?
G of x.
Oh, shit. I don't know why I put a G here, by the way. This could be really messing things up for you. There. Okay. That's supposed to be this guy, right? That's my fault. So this function is what's given to us. And I create an area function. This function is the area under f of x from a to any x, but f of t. Okay, so now you might see why I had to call this a t. There's got to be an x up here. Really strange, right? Really strange. But for example, if my f of t looked like this, let's make, yeah, sure would. Let's make A1. So you guys can handle this. So g of x equals the integral 1 to x f of t dt. What would g of 4 represent? Yeah, so you can rewrite this 1 to 4. Now you can put a 4 in there. And what does this mean here? What does that mean?
The area under the curve from 1 to
Yeah,
4.
this area here. What shape is that area? Trapezoid, kick ass. Could you calculate this area? Could you answer that question without calculus? Yes. If you remember the trapezoid area formula. It's basically, what's the area of a triangle? 1/2 base times height. Isn't that a decapitated triangle? Chop off with his head, right? So the area of a trapezoid is 1/2 the sum of the bases times the height. It looks like 1/2 base times height, but now there's two bases, right? This base and this base. So it would be 1/2 of 1 plus 4, right? 1/2 of 5, and you gotta be careful, the height would be 3. So 1/2 of 5 times 3, so 15 halves. And then what if I said g of 5? Well, you would just make a larger trapezoid, right? Okay, maybe. That function is freaky. Totally is. But do you understand how I'm given, so this function is basically t, right? Because it just goes wee. So I'm given a function, it is just sitting there. That function is not changing. That function is just sitting there. And then I can evaluate the area up to whatever point I want to. That's my variable. How far do you want to go? That's my variable. The rest of the shit is a constant, which is weird. I know. That's why it's such a freaky function. This is how we're going to connect antiderivatives with area. We're going to prove something called the fundamental theorem of calculus, part 1. There is a part 2, right? History of the world, part 1. Okay, I think that's enough. I apologize for the mistake again, but so we basically we just got done with 5.2 and talked a little bit about 5.3. 5.3 is exact stuff. And did everybody see this? I don't know if you came in after I made this announcement. Okay. Make sure people at home see that. Okay. Quiz.